form different types of genome variation, and as I alluded to, how we can take
an actual variety, not like an inverse limit of level.
But reading this article in the newspaper, nobody had a big effect. Hopefully that's making NumPy array that has 1,000 heights in it. If I compare it to a threshold, it's going to take each of the values from the array, compare it to the threshold, and it will either be true or false. So the result of the less than is a logical array that contains 1,000 true or false Boolean values. And now if I take the sum, that seems kind of weird, but it's going to treat all the trues as 1s and all the falses as 0s. So the sum is going to be the number of people who are on the wrong side of the threshold. So this says that of 1,000 men, 164 of them would be misclassified if we tried to label them by height, because they fall below the height threshold. If you replace that with a mean, you make a NumPy call to the method name, it'll get you the average value of all those trues and falses, which is now in terms of a function rather than a number. So either of those is fine, but I'm going to switch back to the way it was before. By the way, Control-Z is a useful thing for doing changes that you make in a NumPy cell. So misclassification rate is one way to quantify what the difference means in practical terms, if you want to communicate it in a way that makes sense. Another way is the so-called probability of superiority, which in this example is a little bit of an awkward term, but it just means that if we draw a random pair of people, I think of this as the junior high school dance problem. If we choose a random boy and a random girl, what's the probability that the boy is taller than the girl? There are a couple ways to compute this in Python. So one way to do this is by lining people up and just pairing them up and computing the fraction of pairs where the female is taller than the male. And you can do that using zip. So if you are more comfortable with Python stuff and you like zip, then you can zip together the male and the female samples, and that's going to pair them up one by one. And for each pair, it'll count the number of times that x is greater than y. Turns out to be about 91%. In the U.S. adult population, if you randomly choose a man and a woman, the man will be taller about 91% of the time. And then if you want to get all NumPy with it, you can do the same thing using the logical arrays that I mentioned. Questions? Tell me whether you've got to the end of the notebook or whether you would like a minute to read about Cohen's effect size before I go on. Got to the end? Would like a minute to read about Cohen? Okay, we will take a minute to finish up the notebook, and then I will do a brief. Okay, two things I wanted you to see here. One of them is Cohen's effect size, which is a way of quantifying the difference in means between two groups. It's taking the means and standardizing them by dividing through by standard deviations. So it's a way of saying the difference between these two groups is some number of standard deviations. The slightly tricky thing is that it's not clear which standard deviation to use, whether it's one group or the other. And you wouldn't want to compute the standard deviation for the whole population put together, because if it really is two groups with different means, then the global standard deviation would be quite big compared to the standard deviation within the groups. So that's why the denominator there is the pooled standard deviation, which is basically a weighted sum of the two, or weighted mean of the two standard deviations. So the details of that are not super important, except that the denominator is meant to be a measure of the variability within the groups. And this is saying that the difference in means is a certain number of standard deviations. The nice thing about that is that the mean is in units of centimeters, in this case. The standard deviation is in units of centimeters. Those two things will always be in the same units, so when you divide them, that ratio, the centimeters cross out, and the result is dimensionless. So Cohen's effect size, one of the things that it's useful for, is making a comparison between different studies. So if I tell you that this study found Cohen's effect size of 2, and that one found that a Cohen's effect size of 1, you can compare those two studies without knowing anything about the domain, without knowing anything about the units that they were measured in. Those things mean the same thing, no matter what. The other reason it's useful is that if I give you Cohen's effect size, you can compute those other two things that I mentioned, the misclassification rate and the probability of superiority. So it's one number that's comparable across different studies, and if I give it to you, you can compute the other kind of important practical things that matter. There's only one drawback to Cohen's effect size, which is that most people don't really know what it is. If you're in a field where it's widely used, you're familiar with it. If not,